Hello everybody, my name is Justin Park. I'm a second-year PhD student at Rensselaer Polytechnic Institute, and one thing we're interested in doing in our labs is reconstructing ancient atmospheres as they pertain to important evolutionary steps in our atmosphere's history. So what I do is I look at ancient atmospheres trapped in halite fluid inclusions. So halite, as we've seen in previous talks, is an evaporative mineral. It forms in these really dry, arid environments where evaporation is the dominating force. As it does so, it can form these things called fluid inclusions, as shown on the top right up here, and they can encapture air or brine in the mineral matrix. Now, these can be primary or secondary, meaning they form at the time the mineral precipitates, or forming some time later with some secondary fluid event. And oftentimes, they form in assemblages of hundreds or thousands of inclusions at once. Now, what I'm interested in doing is looking at the gases that are trapped in these primary inclusions and saying something about the evolving composition of the atmosphere. Now, we do have some evidence for what we think the atmosphere looked like and how it evolved. Here I have plotted one of the major models suggesting the change in partial pressure of nitrogen, oxygen, CO2, and methane as a function of time, starting with the moon forming event 4.5 billion years ago. Now, if you'll notice here, there is a lot of uncertainty in these measurements, and this is due to them being made with indirect proxy measurements. Now, also, in the period between 2 and 1 billion years ago, here, we have this period known as the Boring Billion, and it's aptly named for the apparent stagnancy of the atmospheric evolution. Now, what we're interested in doing is providing ancient atmospheric constraints using fluid inclusions in the period between these 2 points, using direct analysis from 1.4 billion-year-old fluid inclusions. So we can do this by loading our samples into a special crushing device. Crushing them, this ruptures our inclusions, and we can pass the gas directly into a quadrupole mass spectrometer. When we do so, we see peaks in our signal that correspond to each crush. These peaks can be integrated and quantified by comparing to known calibration points. Thus, we can get an idea of the composition and known amount of moles of nitrogen, oxygen, argon, and CO2 present in these inclusions. When we backtrack and calculate the ancient atmosphere composition, we do have to be wary of any aqueous contributions. As we know, Henry's law tells us this atmosphere may also be dissolved in the brine phase in its equilibrium. So when we did this, we saw some variability in our results. Here I have plotted the mole fraction of nitrogen, oxygen, argon, and CO2 as a function of the size of each sample. One thing we can notice is that the primary and secondary inclusions do capture different atmospheres that are distinct from one another. Now, we're very interested in the primary inclusions, as that's the environment that the mineral formed in, and we can compute an average partial pressure or density of each gas and compare it to the modern atmosphere. When we do that, we saw some very interesting things. Back 1.4 billion years ago, we found atmospheric nitrogen was roughly the same partial pressure as it is today. Atmospheric oxygen was around 1/10 as dense, argon was about half as dense, and carbon dioxide was actually 8 times more dense. Now, each of these gases has really important implications, but due to time, I'm only going to have time to talk about oxygen today. So when we looked at our oxygen results, our measured partial pressure revealed some pretty interesting things. Here I have it compared to many of the predicted models that have been proposed. What we saw is that we captured more oxygen than these models would have proposed. This indicates that these direct measurements might be able to capture things that the proxies are unable to. And this has some pretty important implications. The oxygen that we measured is above theoretical lower limits necessary for the early evolution of life, and it's also in agreement with some evidence suggesting there was a developed ozone layer at this time. Now, on the right here, I have plotted a phylogenetic tree showing the marked diversification of red algae in the Mesoproterozoic. Now, red algae are very important as they're some of the first photosynthetic eukaryotes. That gives them an evolutionary advantage to produce more oxygen than their predecessors. And this becomes really interesting when we compare this to our timing of the deposition of our samples. We can see they're roughly contemporaneous, and thus our elevated oxygen measurements are likely due to the presence of these red algae. So I hope I've shown here today that the atmospheric oxygen here is pointing a more dynamic picture of the Boring Billion, and it might not have been so boring at all. We have important implications of these ancient red algae evolving at this time period that led to this. So with this, I hope I've shown that fluid inclusions can capture and maintain direct evidence of ancient atmospheres for hundreds of millions of years, if not billions. With mass spectrometry, we can probe the contents of the gas that are trapped within these, and we can look into how the atmosphere has evolved. We aimed to make compositional measurements of the atmosphere 1.4 billion years ago, and we found something very different than our present atmosphere. Hopefully, in the future, we can make isotopic ratio measurements and see any further evolution trends. So with that, thank you all for listening. If you have any questions, I'd be happy to talk to you at my poster number 14 after this.